Hey guys, Mr. Smith here, and in this lesson, our second lesson of our combining functions unit, we're going to combine functions today by multiplying them or dividing them. In our last lesson, we added functions together and subtracted functions together. And the interactions between two functions, when you multiply them and divide them, a little bit less obvious than when you add or subtract them. And so today we're going to look at a couple of examples of products of quotients of functions, um, tie in some skills we've learned in earlier units, specifically like when we look at the quotient of two functions. Our work in our rational functions unit will come into play. And then we're going to look at a specific example of products and quotients of functions, looking at some marketing strategies for a baseball team. So let's just get into it. So for our first example, we've got two kind of like basic functions, a linear function and a quadratic function. F of x equals x plus 3 is our linear function. G of x equals x squared plus 8x plus 15 is our quadratic function. We're going to combine those. Yes, in our last lesson, we might have added those or subtracted those and saw we got another quadratic function. Today, we're going to multiply them or divide them. And we get drastically different results when we do either the product or the quotient. Or in our first example, we're going to do the product. We're going to look at what the equation is when we multiply those two functions, and then we're going to graph it and see what we get. So let's dive in here. Oh, my tablet's unplugged. There we go. All right. So let's do part A. So part A, y equals f of x times g of x. And f of x was our linear function, x plus 3. And x squared plus 8x plus 15 was g of x. Now, one thing to note here is that x squared plus 8x plus 15 can actually be factored. So we're going to get this function in two forms. We're going to expand it all out, but we're also going to get it in factored form so that we can more easily make a sketch of it. And also, hopefully, you kind of see right off the hop that because we're multiplying a linear function by a quadratic function, the highest power of x we're going to get is going to be x cubed. So we're going to get to review a little bit of stuff from our first unit on polynomial functions as well. All right, let's expand this guy out. So we get x cubed plus 8x squared plus 15x, and then distribute the 3x squared plus 24x plus 45. And that gives us an expanded form, x cubed. The x squared terms would be 11x, and then plus 39x plus 45. So that's the expanded form. A little helpful. We can see what the y-intercept would be. It would be 45, be expanded form. We can see like the leading coefficient is positive and it's an odd degree polynomial. So we know what the end behavior would looks like. But as far as finding like the zeros, that's a little more complicated with expanded form. We'd have to use like the factor theorem to work backwards. But if we just use this step from earlier, we could also get the following, that this product of two functions is equal to x plus 3, and x squared plus 8x plus 15 factors into x plus 3 times x plus 5. And you get this nice factored form, x plus 3 squared. So we can see that we have a 0 of order 2, x plus 3 squared, and a 0 of order 1 with x plus 5. So that'll give us a bit more information about what our graph looks like. So this would be factored form. All right, let's give this one a sketch. Now that we've found the equations, we're going to state its domain and range. So let's just maybe have a little chat about some simple properties so we can just get on there right away. So the y-intercept, not a lot of work to be done there. We can just read it off the equation, 0.45. I might make a more of a rough sketch in terms of the y values. So I'll add that on once I get a little bit better idea of the scale of what's going on. For our x-intercepts, we've already factored it. So we have x equals -3, and that is an x-intercept is 0, a root of order 2. And we have another one, x equals -5. That's a 0 of order 1. So if we recall what that means back in our polynomial functions unit, for x equals -5 with a 0 of order 1, the function is going to pass through -5, but at -3, it's going to kind of bounce back. The function's not going to change sign. And one last piece of information that'll be helpful to draw this, and then we'll just make the sketch from there, is the end behavior. This is also just a little good review lesson tying in some things from earlier units. So our leading coefficient, I'll just say leading coefficient, for this function is greater than 0, and the degree of our function is odd degree, right? The degree of our function is 3. It's a cubic polynomial. So what that means is that our end behavior, if we think about it from left to right, it's going to behave like your basic linear function, your basic cubic function. We're going to be going from quadrant 3 to quadrant 1. We're going to start in the bottom left, and we're going to finish off in the top right. So let's put all that stuff together, get a rough sketch, and then maybe I'll pull up Desmos just as a bit of a confirmation. So we have two x-intercepts at -5 and -3. We'll have an x-intercept at 0.45. I purposely left off the scale there. I'm just going to pop it here, 0.45, just label that. And then I'm going to fill in the blanks with my end behavior. So I know that I start down in quadrant 3 and I pass through x equals -5 because it's order 1. And then I know that we bounce back at -3 because it is an order 2 root, x equals -3. And then I think I can do better with that. And then we're just concave up all the way, just like a cubic function, finishing off into quadrant 1. So something like that, decent enough graph. Let's check out Desmos. So x plus 3 squared, 5 equals x plus 3 squared x plus 5. So we can see it has the end behavior we described. It passes through x equals -5. It has a root of order 2 at x equals -3, so it bounces back. And the end behavior is, as we said, and of course the y-intercept is 0.45, is a bit off the page with this scale, but that's okay. Interesting talking point just for moving forward in your next math course. In your next math course, you'll add a little bit more detail to sketches like these. You'll actually be able to find out using derivatives and using calculus where exactly that maximum point would be. But for our purposes, we just know the rough location of it. But yeah, in your calculus course, you'll be able to find the exact location. That'll be pretty interesting. Okay. The last thing to do is just talk about the domain and range of this function. And there's not a lot to talk about. It's a polynomial. There are no restrictions on x and y. And I'll just pop my domain and range up in here where I have space. So our domain, x can be any real number. Our range, x can be y can be any real number. All right. Kind of a bigger idea of this question too is, you multiply one polynomial by another polynomial, you get another polynomial. All right. Now let's look at what happens when we divide these two functions. We look at the quotient. So we're going to see we get a drastically different graph, looking at y equals f of x over g of x. And f of x, I think, was x plus 3, right? X plus 3, yep. All over x squared plus 8x plus 15. So what we have is a rational function. We have spent some time talking about rational functions in this course. And what we have here is a linear function over a quadratic function. And we could have a lot of interesting behaviors first, but for these types of functions. But what we did see is that sometimes these can simplify a little bit. Sometimes you can factor the bottom, and once in a while you get a factor on the bottom that's consistent or that's equal to a factor on the top. So if we actually simplify this, we can see that. Because we can factor the bottom. We get x plus 3 times x plus 5. I might just go up to this space here. And the x plus 3's divide out. So actually, this does simplify down to something that's a lot easier to sketch, 1 over x plus 5. We just have to make sure we include the restriction here. X cannot equal to minus 3. So there's our function. So it looks a lot different than the multiplying the two functions. This is not a polynomial function. This is a rational function. Originally, it was linear over quadratic. As we can see, though, this does simplify down to just the reciprocal of a linear function. Let's graph it. So I might add a little note just up where I have some space here for our graphing purposes. Thinking about this guy in terms of transformations might make it pretty easy to graph. We have 1 over x plus 5. That's literally just a horizontal translation, left 5 units of our basic reciprocal of a linear function, 1 over x. And that's how we're going to graph this guy. So I'm just going to make a little blurb here. This is just a horizontal translation, left 5 units of the basic function. I'll put that last part in. Y equals 1 over x. Okay, so let's give this one a little sketch. I think I can add, I don't want to add too much detail to this to make it clunky, but I think this will be okay. Just in pink here, I'm just going to graph the original function y equals 1 over x, just maybe as a bit of review. So if we recall, we get a vertical asymptote where the function y equals x would have an x-intercept, and of course that's at x equals 0. And all of the y values are just the reciprocals of the values of the original function y equals x. And that gives us a couple of simple points. The reciprocal of 1 is 1. The reciprocal of -1 is -1. And we get a graph that approaches the asymptotes. I should draw in my horizontal asymptote as well. Those last few are a little. Graph that approaches our asymptotes, kind of like this. I'll just maybe, I think for our purposes, that's pretty decent. So that's our base function, y equals 1 over x, just as a little bit of review. Let's sketch our translation. And what color would be good for that? I might try, I wonder if this will show up well. So everything translates, all the points, and also the vertical asymptote is going to translate left 6 units as well. So the graph of our function, 1 over x plus 5, will just move over those key points, those anchor points. And we'll draw it in. Now, as I'm finishing off here, and of course the horizontal asymptote is unchanged because there's no vertical translation here. What I've drawn is not quite our function f of x over g at x equals 1 over x plus 5, because I haven't quite dealt with that restriction yet. X can't equal to -3. And if you guys recall how that, what that showed up as on a graph when you had a single restriction like that wasn't at a vertical asymptote, it corresponded to a hole in the graph actually. So we're going to have a hole in the graph at x equals -3. So I'm actually just going to put a hole roughly right there for now, an open hole illustrating that. And now we have a graph of our function. And let's actually, it won't take too much work for us to find where the hole is. It's just good review. So let's find out where the hole is. The hole we know is at x equals -3, but as for the y value, that's an awful at symbol. There's going to be a hole at y equals 1 over, if we plug in -3 plus 5, we get 1 over 2. So we can actually just add that little bit more detail. Our hole in the graph is at -3, 1 over 2. All right, and for the domain and range of our function f of x over g at x, so what are the restrictions on x? Well, obviously we stated the one, x can't equal to -3, because it makes the bottom 0 of our original quotient f of x over g at x. Of course, -5 is the same thing. One of those restrictions comes from a vertical asymptote, the other comes from a hole. So we can say, one way to say that, x is any real number such that x doesn't equal to -3 or -5. That would be just fine. And for our range, so what we can see is our graph is going to hit all the y values except 2. There's a horizontal asymptote at 0. So normally for like the function 1 over x, the range would be just y can't equal to 0. But we have a hole at the graph at where we just found at -3, 1/2. So there's actually 2 y values we can't get. We cannot equal to 0 or 1/2. This graph will never touch 1/2. Okay, so yeah, I really like those examples. Like nothing too crazy going on. We're multiplying functions, we're dividing functions. But what you guys can see, like when we took two polynomials functions, we multiplied them, we got another polynomial, we graphed it, we reviewed some ideas from earlier in the course. And when we divide two polynomials, we get a rational function, and we're going to get, we may get vertical asymptotes popping up, holes in the graph popping up. But yeah, just a lot of good connections between a bunch of units. And that's more or less it, guys. Like, I mean, it's dividing functions, it's multiplying functions. There's no real new algebraic skills coming along with this. Just wanted to show you guys the types of functions that kind of pop out when you look at a product and quotient of functions. In this example here, we're going to tie in what we just learned to some more realistic applications. We're going to look at a marketing example. And the three base functions we're going to combine by either multiplying or dividing, they're all linear functions in this case. So let's just talk through this question here. So a baseball marketing team is boosting fan support. They want to get more people at the games. So in this first paragraph here, we can see that they're going to start reducing the price of games. The later on into the season they go, the cheaper the tickets are going to be. So you can see initially they're going to be $25, and every game that's played, their tickets are going to decrease by 10 cents. So just as maybe as the season goes on, and the baseball season is a very long season, people might lose interest. But if tickets are cheaper, you might get more people at games, and you got people in the seats. You can sell hot dogs and beer and like baseball caps and all that stuff. So totally legitimate marketing strategy, makes a lot of sense. Another strategy they're using is they're going to give away baseball caps. And the number of caps they're giving away in hundreds is going to drop down every game that's played as well. So initially they're going to give out 200 caps, and then every game that goes by, they're going to give away they're going to give away 4 less hats, 0.04 per game. And in terms of hundreds, that's 4% of 100, so 4 hats per game. So reducing ticket prices, they're giving away hats, and then since they took these initiatives to get people to come, they have noticed that the number of people attending is changing in hundreds. The number of people changing initially was 1,000 or 1,000, and then every game we're getting 20. We're getting 200 more fans. What we're going to do is we're going to look at 2 situations. We're going to look at the product of the functions p and n to look at that effect, and we're going to look at the quotient of the functions c and n, and just do a bit of analysis. The math isn't going to be too crazy because everything's a linear function, and we're going to be using Desmos to produce a lot of these graphs. So yeah, we're just going to get the equations, make some graphs, have a few conversations, and just do a bit of analysis. Okay, so let's get the function p of g times n of g. P of g times n of g. All right, so p was what, 25 minus 0.1 times g. As we're writing this out, kind of think about in your mind, what kind of function is going to pop out here? Remember, we looked at an example of a polynomial times a polynomial earlier. This is the same thing. It's just linear. It's just 2 linear polynomials, 10 plus 0.2g. So what kind of polynomial function is going to pop out? Well, it's linear times linear, so we're going to be getting a quadratic function. Let's expand this out. So 250. 25 times 0.2, I believe it's 5. Negative 0.1 times 10, that's just negative 1. And then we have negative 0.1 times 0.2, negative 0.02 g squared. I like to put my higher degree terms first. Negative 0.2 g squared. We'll have plus 4g, and finally plus 250. All right, let's head into Desmos and see what this graph looks like. And we're only going to graph it for the range g is greater than or equal to 0, because g is games played, right? It doesn't have any meaning if g is negative. So we'll restrict that domain. And we might have to change the scale to get our entire graph in here. But yeah, let's head into Desmos here. I'll clear off this guy. And we'll do y equals negative 0.02. I'll use x squared plus 4x. Was it plus 4x or minus 4x? Plus 4x plus 250. Plus 250. All right, and of course we can't see that graph. I'd like to change the domain for this guy. I'll worry about that in a second. Let's change the graph to something where we can see this stuff. All right, so for x-axis, let's use, there's like 160 games in a baseball season. That'd be like 80 home games. Let's do negative 10 to, I'll just go to 100, maybe 70. And maybe do a step of 10. And for the y-axis, I don't actually know how high that function gets. So I'll just do, let's do negative 20. I'm just going to guess like 500 maybe. Okay, that actually worked pretty good. We'll do steps of 20. Okay, great. There's a lot of detail there. I would love to, what if I change this to f of x? Can I change the, maybe I can do, nah, we're just going to leave it. So just keep in mind, like we can't have negative games. So we're only really concerned with the games for greater than or equal to 0. If you want to make a rough sketch of this on your lesson sheet, like that's fine too. But my intention is that you're just kind of following along in Desmos. So we've got our graph there. Now let's just talk about the meaning of this graph. We've got the algebraic model, we've got the graphical model, but what does it all mean? So will the owners increase or decrease their revenue under this current marketing plan? So let's go back to Desmos. Think about what this function means. P of G is the price of a P of G is the price of a ticket. N of G is the number of people that come to the game. And so this function, f of G, I might make a little blurb about this. Function we just looked at. It gives the revenue, the money that the owners bring in hundreds of dollars. Right? Because N was the number of people that come to the game in hundreds. And what we can see is from the graph, because this graph is quadratic, initially the revenue they get, 250 hundreds, which would be $25,000. As games go by, the effect of this marketing campaign is very successful because you can see their revenue is increasing and increasing and increasing. It reaches a maximum at about 100 games, and then the effect of this marketing campaign starts to die off a little bit. Eventually the ticket prices are going to get so cheap that even if you fill the stands, you're not going to make as much money if you keep lowering the ticket price. What we can say for sure about this one, let's make a little blurb about the function increasing. The function increases to approximately 100 games, and then starts to decrease. So we can say the owners definitely increase their revenue. Again, it's increasing and increasing and increasing, but eventually, after 100 games, marketing campaign will become less effective. All right. So just the connection between taking two functions and finding the product. In this case, that product had some actual meaning since we were multiplying the ticket price function by the function that models the number of people coming. This combined product function gave us the revenue that the owners would bring in hundreds of dollars in terms of the games played. And as we saw, since it's quadratic, the revenue kind of increases to a maximum and starts to drop off. Because after 100 games, you decrease the ticket price so much, you're just going to start losing money because your tickets are so cheap. For example, I think if we do 25 minus 100, minus 100 times 0.1, that's $15 just calculated. So after 100 games, the ticket prices are $15. Maybe the stands are full, and so there's no point in decreasing the price anymore. Decreasing the price more just makes it less effective. You make less money. All right, let's look at a quotient of two functions. So we're still going to use the number of people coming to the game. We're going to kind of look at the number of caps per game. And this time we're dividing them. We're going to look at Desmos again to get the graph. And again, keep in mind my graph here has values for g is less than or equal to 0, but remember that doesn't make any sense. We're just kind of concerned with the graph from 0 and onwards. All right, so let's look at this function f of g, which is cg divided by n of g. As we're writing this function out, you can try to think about, well, what the last one gave the revenue. What does this one mean? What's this function? If we take this quotient of functions, what's the interpretation of this one? C was 2 minus 0.4g, 0.04g. Again, that was the number of caps we give away in hundreds. So starting off with 200 at g equals 0 and giving away 4 or less per game. And then a number of people attending the game is going up, and it was 10 plus 0.2 times g. All right, great. We are going to use Desmos for this one, but I think it would be useful just because we have time, and we're almost on the lesson. Maybe just quickly go over how to find a vertical asymptote and a horizontal asymptote when you have a linear over linear rational function. For the vertical asymptote, we set the bottom equal to 0, and we'll use Desmos to confirm these details. So 0.2 times g equals negative 10. And so we're going to get a vertical asymptote at g equals negative 50. And we're going to get a horizontal asymptote. Remember, to find a horizontal asymptote for a linear over linear rational function, you look at the ratio of the leading coefficients, which for us on the top, it's going to be negative 0.04, and on the bottom, 0.2. So we're going to have a horizontal asymptote for this guy at y equals, I think that's multiplied by 5, negative 0.2. Although, I think I'm going to check that. Been doing a lot of math today, already taught a class. Yeah, 0.2. We'll just see that when we pop into Desmos. We'll also have might as well just keep going. A y-intercept. We'll plug in g equals 0. F at 0 is going to be equal to 2 over 10, which is going to be equal to 0.2. And for the x-intercept, we set the top equal to 0. I guess this is a g-intercept technically. 0 for g equals 0. 2 equals 0.04 g. And 2 divided by points, that's 2 times, I think it's 50, but again, I'm going to double check. Yeah, 50. Okay, just nice to have all those details so we can confirm in Desmos. So let's actually bring back Desmos. And I'm going to I'm just going to refresh and just clear everything off here. And we're going to type in, I think it'd be informative to type in the individual functions too. So I'm going to call c of x 2 minus 0.04x. And you should open up Desmos and follow along and do it with me here. And I'll call capital N of x, number of people, 10 plus 0.2x. And drag, we can see both of those linear functions here. Where can I put myself some out of the way? Over here. Okay, and then we called f at x, it was c at x over n at x. Okay, good stuff. I'm going to just move my graph over here. Okay, and maybe change the scale up a little bit so we can see more of what's going on. Let's try for our x-axis. Let's try keep the kind of the same number of games. Let's go negative 10. Let's just go to 150 this time with a step of 10. And for our y-axis, let's go not sure how this is going to play out. We'll just experiment and see how it looks. Oh, that looks pretty good. I think we'll just keep it just like that. All right, so we saw the original two guys were just linear functions. You can see actually that the cost function or the cap function gets to 0 at 50, which makes perfect sense, right? Because after 50 games, you're not giving away any more hats, right? And the other function's a bit too high off the graph, 10 plus 0.2x, but we saw that was just linear. It was just increasing over time. Number of fans is increasing. So here we have our rational function. So we got the x-intercept and y-intercept that we talked about. We're not really concerned with the graph below or past g is less than 0. So we can't really see what on the graph where our vertical asymptote was, but we said it was at negative 50, and negative 50, it certainly seems that negative 50 could be reasonable. And we said our horizontal asymptote was at negative 0.2. Again, certainly very reasonable. In fact, I think that one we could probably even see pretty easily. If I go to like negative 0.3 or something, yeah, you can see it's leveling off, and it's eventually going to hit 0.2. All right, let's talk about this function though. What is it actually telling us? So on the top, we have the number of hats. On the bottom, in hundreds. In the bottom, we have the number of people in the game in hundreds. So what this function actually represents, caps over people, it's like the number of caps per person. It almost represents like a likelihood of getting a cap if you go to the game. So for part B, we were asked to talk about explain what it means and how likely are you to receive a free baseball cap if we attend game 5. So let's check this out. All right, I'm going to record a little blurb here. So this function gives the number of hats given out divided by the number of fans. What it essentially does, it gives you like a probability or a likelihood of receiving a hat at that game. For example, if the top was like 2 and the bottom was 100, there's 2 caps given out. There's 100 people, and so your chance of getting a cap would essentially be 2 out of 100 or 2%. This function, no S, gives probability or the likelihood of receiving a hat if you go to that game. So let's look at what our function is at game 5. So I'll call that F. Call that F in the original question. So F at 5 for us is going to equal to, let's just plug it in. So 2 minus 0.04 times 5 divided by 10 plus 0.2 times 5. So 2 minus 0.2, that'll be 1.8. 10 plus 0.2 times 5 is 1.8 divided by 11. And let's just get that approximately as a decimal. So 0.164, or as a percentage, 16.4%. So remember, the cap function was in hundreds, so 180 caps are being given out. The bottom is the number of people at the game in hundreds, 1,100 people there. So whether we do 180 divided by 1,100 or 1.8 divided by 11, we still get 16.4%. This is your chance of getting a hat if you go to that ball game. And as we see from the graph, this probability is decreasing over time because as the games go by, they're giving out less caps and there's more people there. So if you want to get a cap, you're best to go earlier on. You might have to pay a bit more for a ticket, but that's the trade-off there. Okay. I just wanted to look at one last very quick example, kind of like modeling a physical process. and to talk about damped oscillations. So you guys know, like if you're on a swing or you just hit a pendulum back and forth, like a kid on a swing is not just going to swing back and forth forever if they don't push or if they're not getting pushed or anything. Eventually, those oscillations they just start to dampen and not get as big and not get as big, and eventually they just settle down. We know how to model this periodic behavior with sine functions, but how do you model periodic behavior where the amplitude is decreasing over time? Well, we can actually use products of functions. So we know that a function that models oscillations would be sine of, I chose sine x would work, but I chose sine of pi x because the period would be 2 pi over pi. The period would be 2. So I can make a little sketch of this. So I will. Sine of pi x has a period of 2, comes back to the axis every halfway, so every 1, and has a maximum of 1. So I'm just going to draw, I don't want to make this graph too cluttered. So I'll just use a dashed line here. All right, so this is f of x equals the sine of pi times x. So that models oscillations. If you want to model something that's decreasing over time, you could use a decreasing exponential function like 2 to the power of negative x. I'm going to draw that one right now. 2 to the power of negative x has it's just like 2 to the power of x, but it's reflected in the y-axis. So just decreasing. I think I'll use the deep purple for this one. Has a y-intercept of 0, 1. And at 1, we'd be at 0.5. At 2, 0.25. At 3, 0.125. And what we get is a decreasing exponential function. And that might be the best I'm going to do. So I'm not going to mess with that. A decreasing exponential. There we go. So what does the product of these two guys look like? So it's really neat. The product of these two guys, which would be 2 to the minus x, to the power of minus x, times sine pi x. What would that function look like? Well, that function will look like a periodic function. It's going to have maximums and minimums, but the maximums and minimums are going to be bound by the magnitude of that exponential function. So here's what I mean by that. I'm just going to sketch a dashed line, that reflection there, down like this. Of course, this was the function g of x equals 2 to the power of negative x. And now I'll pick, let's use green here to show what this will look like. So the product of these two functions is going to have the same x-intercepts. Wherever f of x was 0, h of x is going to be 0 as well because it's a product. And what's really neat is wherever that sine function had a maximum, our h of x function will have a maximum too, but the maximum will be bound by this curve 2 to the power of minus x. So minimum here will be on this curve. This maximum will be on this curve. And that's a pretty good, I think that's enough. What you can see is you get this periodic behavior, except the amplitudes are going down. This is what we call damped oscillations. And essentially they get to near flat. So I thought that'd just be an interesting application to share with you guys. If you get into physics, you'll certainly be looking at damped oscillators, and the math behind them is just simply a product of two functions, a decreasing exponential and a sinusoidal function. All right, so that was I enjoyed giving that lesson. Hopefully you guys enjoyed doing it. So we looked at today product of two functions, and what we saw was that essentially finding the product and quotient of two functions, we start to tie in a variety of skills from our earlier units, polynomial functions and rational functions, and then we hopefully are convinced that these can be applied in a variety of situations. We looked at two, baseball marketing and these damped oscillations. As usual, guys, I have some suggested practice for you to try. Please reach out if you need a hand. Be glad to chat with you. Okay, that's it for me, guys. Hope you're having a good day. Take care, and we'll see you soon.